While I'm making these beautiful Google slides, the JIT is working hard in the background, protecting me from remote attacks, when things go right. If the JIT compiles code incorrectly, though, it can introduce exploitable errors that attackers can take advantage of to compromise victim machines. Errors can happen at any stage of the compilation pipeline, from optimization to code generation, but we're going to focus on bugs in range analysis. Range analysis is how compilers figure out what values a variable can take on at a given program point. The JIT uses range analysis to do optimizations like bounds check elimination. Here, the range analysis deduced that x is always 3, so the compiler can remove the bounds check. If range analysis is wrong, though, bounds check elimination can be wrong, which lets web JavaScript read and write memory out of bounds. To prevent this, we developed Vera, a way for browser developers to prove their range analysis routines correct. Come to my talk to hear more about it.
Hello, my name is Gregory Duck and I'm from the National University of Singapore. I'll be presenting Binary Rewriting Without Controlflow Recovery. The basic aim of our approach is to rewrite binaries without moving existing instructions. And to do so, we're going to use an old technique, which is to replace instructions by jumps to trampolines which implement some patch or instrumentation before returning Controlflow back to the main program. This approach is reliable and scalable, but only works if the instruction is large enough to be replaced by a jump. For small instructions, this approach cannot be directly applied. In my presentation, I'll be presenting some new techniques such as instruction punning, padding, and eviction that can insert jumps to trampolines for instructions of any size, including single byte instructions. If you wish to find out more, please join my presentation. Thank you.
Blanket library deploading. Security continues to be a never-ending game of cat and mouse, so what can we do? Well, we know that software systems still rely on C and C++ libraries which lack memory safety. Applications linked with glibc, for example, become exposed to attacks like denial of service, code injection. And we know that deep loading allows you to get rid of potentially harmful code. Static and link time techniques, however, are conservative and leave substantial attack surface intact. But ML-based approaches are aggressive and unsound, and they all try to cut code, so we flip the problem and bring in only what we want. Here's how it works. Imagine function foo and its callees, blanket at program start, execute. Now the program may need to call foo, so we link it plus the functions we expect it to call. It executes, then we blanket again. This gets about 97% attack surface code reduction. So how do we handle the complex call graphs and flow, the limitations of program analysis? How do we solve the problem at the binary level? How do we construct key runtime optimizations? Here's a hint. We use a unique predictive approach based on ML and program analysis. Please come to the talk for details.